Okay. Okay, so today what we will do is we will start with a new unit, and it's regarding model evaluation and hyperparameter tuning. And previously, we also, in our previous discussion, we also learned some of the model evaluation hyperparameter tuning. It's just not that systematically, okay? So what today we will do is systematically learn. The first concept is, if you recall so far, what we have learned is, in some cases, you need to do data scaling, feature scaling. It's about feature scaling so that it can better fit the model, especially if you recall for gradient descent. Okay, so that's regarding feature scaling. And feature scaling, generally, we discuss two approaches, normalization and standardization. Okay, so that's regarding scaling. And after scaling, and sometimes we also need to do dimensionality reduction. And if you recall, we also discussed some technique like PCA, LDA, okay. And after that, then we can do training, okay. So with some learning algorithm to do the training. And after training, then we do the prediction, okay. So that's generally speaking the steps. And with sklearn and for scaling, then you need to do fit and transform, is it? And dimensionality, we also do fit and transform, okay. And then we do the fit, okay, with the learning algorithms, okay. And so it's like a kind of discrete step for each of it. And for sklearn, in sklearn, we can do pipeline processing. Okay, so basically it's we can streamlining the workflows with pipelines. Okay, with pipeline. So we don't need to write one by one individually. We can do pipeline. Okay. And also, if you recall label encoder previously, we also learned, okay, is to convert the from string to integer, okay, for the data feature or target value. Okay, so that's the first one regarding pipeline. So next, let's take a look at our code, okay. My code. Where is my code? Okay. And this example is also on our course website. Okay, it's from chapter 6. So the data set we are going to use is that Wisconsin breast cancer data set. Okay, and here we have a glimpse of that data set looks like. So looks like there are about 32 columns. Okay, so if we exclude the second one, looks like it's regarding classification. Okay, so probably around 30 features. So the data shape, the total number of records around 569. Okay, and then we need to do, because over the data set we have some strings, so we need to do the conversion from string to a value. So that's And also, if you see the features we take from the third one, okay, and the target is the second column. And for label encoder, we are going to apply it, so fit transform for the target value, etc. So then it's transformed from benign and malignant to 1 and 0, etc. So that's regarding this part. And then what the next part to try to show is the train test split. So this one we already quite familiar, okay. And for the stratify, if you recall, it's when you do the training and the testing split, you maintain the class ratio as the original, okay. So this is the train and the test split data. And then what next one try to show is how can we combine the transformer and estimator in a pipeline, okay. So here we are, for the feature scaling, we are going to do the standard scaler. And for the dimensionality reduction, we are going to use PCA, okay. As a model, we are going to use a logistic regression. So for the pipeline, then you need to import that to make a pipeline, okay, from the pipeline package. So over here, then we just call the make pipeline. Then did you see, you just plug in the pipeline, the step by, the stage by stage, the training processes. So first we do scaling and then do dimensionality reduction and then do model training. So we make all of them into this make a pipeline, okay. And then we are going to fit the training model, the training data we are going to fit. And then we can predict with the testing data. And here is the testing score, okay. So you can see with this make a pipeline, it saves a lot of our coding work, that we don't need to write for each step. Then we need to do transform, fit transform, fit transform. Okay, and then the next one, let's move to another new concept. And then we come back to okay, for the next concept, the first one is regarding bias and variance trade-off. And if you recall previously, we already discussed this quite often, is it? And the variance, it's basically the spread out of the data set, is it? For the variance. So basically it's a measure of what? Measure of how far the observed value is going to differ from the average of the predicted values. Okay, so that's regarding variance. And we would like it to be low, okay? And that low variance can be quantified by R2 score in statistics, okay? So R2 score can be also used to measure the variance. So what is the R2 score? It is total variance explained by model over what the total variance, is it? And if you recall, when we discuss PCA, we discuss the explained variance, is it? So that's based on the model, based on the model, and the total variance is the original. But over here, so this R2 score is regarding any model, okay? And measure a metric to measure how good your model is. MSE is a mean square error. Okay, so average of square of errors. Okay. And here it present the bias and the trade-off, and the bias and the variance, the trade-off. Okay, the trade-off, and we try to minimize the mean square error. Is it? Okay, so here give different scenario. Is it? And the target, the center part is the most accurate. Is it? And the dot are the sample distribution. Okay, so for the first one, it's low bias and low variance. So that's the ideal scenario. Is it? Then you can see the samples and the precise kind of match with each other. Is it? So that's this case. Okay, then for this case, it's low variance but high, or low bias but high variance. High variance, we can clearly see the sample distribute quite a lot. Is it spread out a lot? Is it? Okay, so, but it's still not too far away off the precise one. Is it? It's still, you see, around the circle, but spread out quite often. Okay, so that's a low bias and high variance case. And then in this case, a high bias and a low variance. You can see the samples kind of clustered pretty tightly. Is it? But they are off the precise model. Is it? Quite a lot. Is it? So this is not good. Is it? And the last case is high bias and high variance. Is it? So then in this case, the data sample on one end, it's spread out a lot. On the other case, it's also far away from model. Is it? So that's why it's a high bias and a high variance. Okay. So this is regarding the bias and variance trade-off. Okay, trade-off. So we would like to have low bias and low variance, but sometimes if we cannot, then we need to find the balance. And here it also explained, normally if high bias, it can be caused by what? Is it? It's the systematically under or over predict the target value. Is it? It's result either the assumption, so your model itself, is it, is not good. Is it? So your choice of model, or you have bias in the training data set. So maybe a training data set, the ratio may be lean toward a certain pattern. Is it? So that can also cause bias. Okay. And the variance, so variance, high variance can cause overfitting. As overfitting means it fit your model pretty well, but when new incoming random data set comes, then it's because it's measures spread out, then it's further away from your model. Okay, so that's regarding variance. And generally speaking, variance can be caused by what? By a complex model. Okay, can introduce high variance. Okay, and it says low bias, is it? And but a higher bias can cause the underfit. Okay, and the oversimplified model can also cause underfit. Okay, and having low variance, is it previously we also said, is it, and with a higher bias, is it, and that can cause, because it's lacks the tool to capture the trends of the data. Okay, so this is the overall about variance and bias. And this diagram explain the better about the variance and the bias related with model complexity, and the y-axis is error. Okay, so error, the low means the result is good, the high means the result is not good, is it? And the model complexity can be like features, more features, is it? Or like, if you recall previously, to try to have more features, you can manually like introduce the polynomial term. With correlated, is it, or high order, is it? So that can make your model very complex. Okay, and in this diagram we can see, is it, the more complicated your model is it looks like the bias can going down. Is it, if your model is too simple, then you cannot catch a lot of features, is it, about certain pattern. So then the error is high. But with the model complexity increase, then the error rate can be lower. Okay, so that's regarding bias. And for variance, then variance is if the model is too complex, then it fits good for the model, that for the sample, but not for the training data, but it's not good for the new incoming data. So it may not be able to catch up a lot of noise, etc. So that's why the error can go up, is it, with the model complexity. Okay, so we can kind of see from this diagram, is it, the best optimal, is it, is both the variance and the bias not too high, then the model complexity, is it, is also not too high, but you have certain level, is it? So this area is best fit for the trade-off between the bias and the variance. Okay, and so there are a couple of approaches. Okay, we can techniques can help relieve the imbalance between bias and variance. One is like the cross-validation techniques. Okay, cross-validation, we will see one is called hold-out cross-validation. The second one is k-fold cross-validation. Okay, and the cross-validation, it's still on all of your original data set. Okay, but it can help us obtain reliable estimates of the model's generalization performance. Is it? And here we say generalization means like not overfit, is it? So how well the model, or like the underfit. Okay. So for the holdout cross-validation, it's you're going to split the original data set into training and the testing. And within the training, we are also going to add a validation set. Okay, and the validation set, so it's going to be 3 data sets. So far we learned is split. It's training and testing, is it? And here we are going to do furthermore, we're going to add a validation. So we're going to have training and the validation and the testing data set. Okay, and the validation is for what? Because if you recall previously, we also learned we needed to tune parameter. Is it tune parameter and compare parameter, if you recall, like regularization. C, is it? And for kernel trick, we also have that gamma. Is it? So those parameters, those are called hyperparameter. Is it? So we wanted to find the best one that can give us the best result. Is it? So for that, if we add validation, that can help in that regarding. Okay. So then let's see what is called a hold off cross validation. Okay. So here it shows the original data set. That then we previously as we split into training and the testing. Is it? And the holdout is for the training part. Then we split. Is it into further split into training and the validation part? Is it a further split? Okay. Further split, the validation is for what? As you can change the hyperparameter and then kind of retrain with a new set of hyperparameter. Is it? Then you collect the performance metrics. Is it? And then you find the best one. And then for the best one, after we find out, is it? So for the validation, so it involves a number of sets of parameters. Is it? And then you pick the best one. Pick a best set. After we pick the best set, then we can do the test. Is it? Then for test, then this whole training data set, we kind of already used it for pick the training. We already split it into the training and the validation, is it? And we pick the best one. Is it? After the pick the best one, then we can use the best set to train the model again. Is it? And find and then also do the testing. Okay, and because over here, it also involves, so this set is to do the hyperparameter. And if you recall previously, like what we learned, like a perceptron, logistic, and SVM, is it? Those we use gradient descent. And for the gradient descent, the goal is to find the best weights. Is it? So weights, basically, it's also some kind of parameter. Is it? So your model training also needed to pick the best weight. Is it? So over here, the idea is this part, you pick the best set of hyperparameter. After you do that, then you pick the model, that you find the training is going to use those hyperparameter to find the optimal weight. Okay, once you find optimal weight, then you can conduct the testing regarding the accuracy. Okay, so that's the general flow. Okay, So this is regarding holdout. And for the cross validation, so here is validation. Okay, the second one is called k-fold. Okay, k-fold, because with just a holdout, so sometimes it can still cause bias because it depends on how you split the data into the training and the validation part, is it? So in order to avoid the data splitting part of the error, is it? We do k-fold. So k-fold, the general idea is regarding the training set. So here it involves number of iteration, if you see here, is it? So over here, we divide it into 10 folds. For the 10 folds is what? Is you have 9 folds kind of training, then this fold is for validation. Okay, so basically this is for validation. Okay, for the validation. And then you repeat, because if you hold out, then you just pick this one. So that may have some bias, is it? But this time, the validation, you see, so across your whole training data set, is it? You are going to have validation. And so every sample is going to be used both as training and validation, is it? So that we can kind of avoid the bias. And then with this, for each of it, you're going to have some performance matrix, is it? Then we are going to pick the average one. Okay, we're going to average all of them together. Okay, and we find the average one, and then we can get the best parameter. That then further on we can do the testing. Okay, so this is regarding k-fold. Okay, and with this k-fold, then let's go to take a look the coding part. So for the coding part, the first one for the cross validation. Okay, so here it's regarding cross validation. So for the cross validation, the first one is also from model selection. It's regarding stratified k-fold. Okay, and the stratify, previously we also learned, it's try to preserve the ratio. Okay, when you do the split, is it between training and testing? Okay, so preserve the ratio of class, because you may have one class over the other class, it's not 50-50, is it? It's maybe 60-70 or 60-40 or 70-30 somewhere. Is it? In that case, when you do split, you want to keep the ratio. Okay, so that's stratified. So for this stratified k-fold, is it? Then we said, okay, we want to have 10-fold. Then you can do the split, is it? And what this example try to show us is then for each fold. So this k-fold, then it will record each fold's information. Okay, so we can do loop, and then for each fold, so here is for each fold, we train with our pipeline model. So that is previously we already pipelined, is it? Everything for the model, and then we do fit, is it? And then we do what? Then we can collect its score, okay, regarding the testing part, is it? And over here, so this fold is a list. Then we are going to keep appending the new score to the list. Okay, to the list. And then we can do the bin count, okay, for so this is just the number of data between each of the class. So here we just have two class, malignant or benign. Okay, and then we can also collect the mean and the standard deviation. Is it? And here is the output. Is it? So for each fold, is it for each fold? Here it gives us the class distribution. Is it? So benign and malignant. Is it? And also give us the accuracy score. And you can see the accuracy score is not the same. Is it? It's different. Is it? Okay, so this is tenfold. And then we can also find out their average and the standard deviation. Okay. So this is regarding k-fold. And what next one try to show is we can also call the cross value score. Is it the cross validation? Okay, so this is regarding cross validation. And cross validation, if you want to use it, then for the estimator is our model. Okay, the learning model. But you can see it's not just a learning model it can take. It can also take a pipeline result. Is it? And then you just plug in this training data. Is it? And this is number of folds. Okay, you want it to be split. And here further again, it can give you all of the scores for each fold, basically. Is it? And here you can also collect the mean and standard deviation. Okay. And over here to also explain, if you recall, that within the cross validation, you can also, this in our previous learning, we also, example, we also saw that, is that the number of jobs and job parameter, is it? And then over here it says, because in this case, 10 rounds basically it's all independent, is it? So you can kind of like a parallel processing, is it, to speed up your training, is it? So in this case, so it can be allowed to be distributed to more CPUs. Okay, and it says if you set it to -1, then you can use all available CPUs. Okay, so allow basically it's just a parallel computation here. Okay. Okay, and then the next, another new concept, learning curve. So let's take a look, the concept part. Regarding learning curve and the validation curve, okay. What are all of those, okay? And so this is also during the process when you try to find how the model can fit, is it? So during the process, we can also use a learning curve, because otherwise, if we don't use the learning curve, if we find out like the model is not ideal, then sometimes maybe you have too few samples. Then you may say, okay, I need to collect more samples. But this sometimes may be very expensive, is it? So a lot of time we can use a learning curve then to help us to diagnose if our model is doing good. Okay, so here it gives us the different scenario. So the learning curve is regarding what? Learning curve is regarding, so number of training samples versus the accuracy. Okay, versus the accuracy. So here is the accuracy. Okay, This is accuracy, this is number of samples. Okay, and in this diagram, so over here, this is desired accuracy. Suppose you said, okay, I would like my model reach 95% of accuracy, is it? And then in this scenario, for this curve, this dot one, okay, this is regarding training accuracy. And for this blue one, this is for the validation accuracy. Okay, accuracy, a validation part. Okay, and we can clearly see both training and validation far below the desired one. Is it far below? Definitely, it's because of high bias. So the model is not good. Is it? And then the second scenario is, so here is a desire. So your variance, this is a training. So the training accuracy is pretty good, as it's all above the desire. But for the validation part, it's far below, is it? So this is validation. So the gap between training and the validation is large. And one is above the accuracy desired one, and the other is below the desired one. So then this normally is caused by high variance. And the high variance, then some reason can cause the high variance is what? Is a model is maybe too complex. Is it model too complex? Then maybe you need to do some feature extraction, feature selection, is it? Feature engineering, is it? We need to do some feature engineering. So the dimensionality reduction, is it? So maybe you can use like PCA, is it, to reduce the dimensionality, or you can use feature importance to only select important feature, if you recall previously in decision tree and the random forest. Is it? We learned like feature importance. You can collect the feature importance, is it? And then you can filter out some lower contributing factor features. Okay, so that's overfitting, is it? And the best scenario is what? Is with the number of increasing the number of training samples, the samples, is it? Both the training, and the validation, the accuracy getting close to the desired one, is it? They are all pretty close to each other. Then this is the best cases, best scenario. Okay, so this is regarding learning curve concept. Okay, and we already, I already explained the learning curve, high bias, high variance situation. Okay, and what is validation curve? Okay, validation curve is, if you recall, we also needed to tune those parameters. Is it like the regularization parameter, like the gamma? Is it? So the validation is regarding accuracy versus those hyperparameter. Okay, so we can also vary the value of model parameters. Okay, and then find out the accuracy relationship with the parameter. Then we can pick the best fit one. Okay, so this is regarding validation. And then next, let's see the example. Okay. Okay, the first is regarding the learning curve. Okay, the learning curve in sklearn from its model selection, we can import learning curve. So here, with what we are going to do, we are still going to do the pipeline. Okay, and here we just do feature scaling, and then we pick the logistic regression. We didn't do the dimensionality reduction for the pipeline, okay? And after that, so this is your model part, is it? Then you can just directly call learning curve. And for the learning curve, you plug in whatever the model, okay? And over here is we have the pipeline model, and then fit with training data, is it? And if you recall, learning curve is regarding number of samples, is it, versus accuracy. So that's why the training size, we need to change it, is it? So in this case, you can split based on, so line space is from 0.1 to 1.0, is it? So this, you're going to split it like 10%-ish, 10%, then 20%, 30% to 100% of all samples. The samples. Okay, the samples. So that's a learning curve. So you can specify how you're going to split. And here we also regarding the across validation fold, is it 10-fold? Okay. And then what we can collect, you can collect the training size, the return, is it how many samples, and the score, training score and testing score, is it? Then we can plot that diagram, and then can give us good visualization, is it? And over here, what we are also going to do is, we are also going to find the mean and standard deviation, okay, of the scores for both training and the testing, okay. Then we do the plot. Okay, for this plot, we do the training size and the mean, okay, the mean one. And for this one is we plot the one standard deviation, okay, from the mean. So we are also going to have this range be highlighted, kind of, okay. So that's what this part is. And then we just plot that, is it? Okay, and then let's see. So here is the result, is it? So number of training samples versus accuracies. We also do the grade, is it? So this is the training one, is it? And here is the validation one, is it? And if you recall, we also plot the standard deviation one, is it, regarding the validation, okay? So then this is the learning curve. And from this learning curve, you can kind of see, is it? So the training accuracy and the validation accuracy, it's pretty close. The gap is very small, and also both kind of reach to certain range and quite high, is it? So we can kind of see, okay, so the number of samples, then in this case, also you can see it's kind of, once it's crossed 300, it's kind of not a huge difference, is it? So a pretty good sample size for these cases. Okay, and then what next one is to see the validation curve. So same thing, you need to import a validation curve, okay? And the validation is regarding some parameter. Is it like the C parameter, like the gamma parameter? Is it? So then in this case, we can specify the parameter range. So over here, it's from 0.001 to 100. Is it? And then we can plug in with this validation curve. So you plug in the model, training model, and the parameter you also need to specify. Is it what parameter? Is it regularization or gamma or something else? And the parameter range we already provide. And the split number of the folds. Okay, after that, same thing is that we can collect the training score and the testing score. Okay, and then similar concept, we do the plotting. Okay, and the plotting, the range is it, and the testing result. Okay, so then over here, this gave us the validation curve, is it? So here the x-axis is the parameter C, and the y-axis is the accuracy, is it? So from this one, you can see the parameter C value, because when it goes to large, then the gap between these two increase. So definitely it's not good, is it? So we can kind of see within this range, it's a good match, okay? Because the gap between the training and the validation are not a lot, is it? So it's the better range is between 0.01 to 0.1, is it, for parameter C, okay. Okay, so this is regarding validation curve. And we only have 2 more minutes, so let's just stop